thank the organizers of this meeting for the opportunity to speak here today. So what I'm going to talk about is some recent work on stress center fluctuations. And just a moment. There we go. Okay, I can scroll that way. So first, let me start by talking a little bit about some of the roles of the stress tensor. So, of course, as everyone knows, in classical physics, it describes both energy densities, fluxes, and forces on material objects, but it also acts as a source of gravity through Einstein's equations. And both of these features will become important for us. And of course, in quantum field theory, this becomes an operator. And the key point that's going to be of interest to us is that the physical eigenstates, the vacuum state and other physically realizable states, are in general not eigenstates of a stress tensor operator. So that means that there will be necessarily be fluctuations. So, and some of the effects of stress tensor fluctuations are going to be, first, there will be force fluctuations on material objects. That will be one of the ways that one might try to test some of these ideas in the laboratory. But from the point of view of relativity, another issue is that these will lead to fluctuations of the space-time geometry of the gravitational field, what I would call passive fluctuations, driven by fluctuations in the source. And these, of course, are certainly distinct from the fluctuations due to the dynamical degrees of freedom itself. But I would argue that these passive fluctuations are still a type of quantum gravity effect and something that will need to be included in a more complete quantum theory of gravity, and hence are of interest for understanding quantum gravity. Okay, so first of all, some basic features that these fluctuations will have. So the quantum these are generally quadratic operators. So in order for them to be meaningful, they need to be averaged over a finite space-time region. That is otherwise, in fact, the fluctuations cannot be meaningfully discussed. And what's more, once you do this, you'll find that the odd moments, typically like the expectation value of the cube of the averaged operator, are non-zero. So you're definitely going to have a skewed non-Gaussian probability distribution. And the final key feature is that it's been known for some time that there are what are called quantum inequalities, which are lower bounds than the expectation values of of things like energy density that are classically positive. Now, in quantum field theory, you can actually find states in which the energy density is locally negative, which would violate the classical positivity. But there are strict limitations on how negative it can be. And these are the quantum inequalities. And you can view these quantum inequalities as basically representing the lowest eigenvalue of the averaged operator. That is, of course, as we know from quantum mechanics, the lowest eigenvalue is the smallest expectation value that you can ever create. But it's also the lowest outcome that you can get in any measurement on a given quantum state. So the probability distribution will tend to be bounded below, but not necessarily, but in general, not bounded above. So here I'll discuss a simple example, which Chris Fuster and Tom Roman and I developed, found several years ago in two space-time dimensions. So this is a massless scalar field in two space-time dimensions. And X here is the average, U is the energy density, the averaged energy density operator. So of course here what we've done is we've taken the normal ordered TT component of the stress tensor and averaged it in time. In this case, it doesn't need to be averaged in space, just in time, with a Gaussian probability distribution with a characteristic width tau. So X is because we're in two space-time dimensions, and energy density times tau squared is dimensionless if H bar and C are set equal to 1. So X is the dimensionless energy density. And we were able to find an exact solution to the probability distribution in the vacuum state, which is given by this form here, provided X is greater than or equal to minus 1 over 2 pi, 24 pi. This is the quantum inequality bound. So of course, the probability distribution is strictly 0 below that. And above that point is given by this formula here, which you notice has an integrable singularity in this particular case as you approach the quantum inequality bound from above because of this negative exponent here. So the probability in this particular case can be plotted. The vertical line represents the quantum inequality bound. So it is actually the density blows up, but of course it's only integrals of the density that are really important. They give the probability of finding an outcome in a given interval. And those are all finite because of the integral nature of the singularity. And of course, then the probability falls off slightly more rapidly than exponentially at large values of the energy density. Interestingly enough, in this particular case, when you calculate the area under this curve, you find that there's an 84% chance in a given measurement of finding a negative outcome. That is, although it's not obvious from this picture, the integral, of course, under this curve is 1. It's going to be a normalized probability distribution. The integral between the lower bound and 0 is 0.84, which leaves only a 16% chance of finding a positive outcome. But of course, the positive outcomes can be much larger in magnitude. So the mean value of a set of measurements will be 0. Okay, in four-dimensional space-time, the situation gets a little more complicated, and that was explored in several papers, starting with one with Tom Roman and Chris Fuster, and continuing with a couple of other papers in collaboration with Chris Fuster. So again, we're going to average so we're going to imagine T here as a generic operator, such as a component, such as the energy density or some other operator that we're interested in. We're going to average it over both space and time generally. And we'll let the characteristic width of the time sampling be tau and the space be L. And these, of course, look a little bit like the test functions that Bob Wall talked about in his talk. But here, we're going to give them a physical interpretation. We're thinking of these as not necessarily just being a means of getting well-defined operators, but they're also supposed to represent the outcome of physical measurements. That is, a physical measurement of the energy density, for example, should take place in a finite region of space and time. And also we expect it to be a finite region. So we require these to be compactly supported functions. That is, that both f and g should be strictly 0 outside of finite intervals, because we want them to represent a measurement that began and ended at finite times, is confined in a laboratory of finite extent. So that's why they're compactly supported. We also require them to be infinitely differentiable, so not to have any cusps of any type. But of course, this means they're necessarily non-analytic functions because of the compactly supported nature. Okay, so We'll also be, in the purpose of this talk, I'm going to talk primarily about flat space quantum field theory. But much of what I say here could be carried over fairly easily to curved space-time. So I'm going to be interested in quantum fluctuations of the averaged operator in the vacuum state, and assume it's a normal ordered operator, so the vacuum expectation value vanishes, which of course means that the average outcome will be zero, but we can get both positive and negative outcomes in individual measurements. And we're going to seek the probability distribution, P of T bar, for measurements in this state. And one way to approach this is through calculations of the moments. That is, take T bar, raise it to the nth power, take that expectation value in the vacuum state, and that'll be the nth moment. And we'll discuss this in a little more detail a little later, but if the moments do not grow too rapidly, then the probability distribution is uniquely defined by the set of moments. And if we, for a moment, consider the case of a free field, a linear operator, such as the electric field, then it's well known that the probability distribution is a Gaussian function, which is determined just by the variance. Those all the higher moments are determined, in fact, can be expressed in terms of the variance, the second moment. And it has this familiar form for the probability of for example, the average quantum electric field operator will satisfy this Gaussian probability distribution. But we're primarily interested in quadratic operators, such as stress tensor operators. But in much of what I'm going to talk about, we're going to take a simpler operator, which is the square of the time derivative of massless scalar field. And this, of course, is a constituent of the stress tensor for the massless scalar field. You can express phi dot squared in terms of a particular linear combination of stress tensor components. And it will have all of the characteristics of, say, energy density or other more physically interesting stress tensor components. So here we consider a massless scalar field quantized in a finite volume with periodic boundary conditions and expanded in the conventional way in terms of plane wave normal modes. So for the case for any quadratic operator, the normal ordered operator will have this generic form in terms of the creation and annihilation operators. Because it's normal ordered, we have A dagger A terms here, and then we have these off diagonal terms. And in the specific case where the operator is normal ordered phi dot squared itself, then the particular forms of these matrices Aij and Bij are given in terms of Fourier transforms of the sampling function. So f hat of omega is the temporal Fourier transform of the time sampling function f of t. G hat is the three-dimensional spatial Fourier transform of the space sampling function g. And we get these particular combinations here. So in particular, the second moment takes this particular form. And we can see that basically space averaging is optional here. It's okay to take the limit at which script L goes to 0 and average only along the world line of a particle. But it is essential to average in time. I should mention, if we go back for a moment to the linear operator case, the Gaussian arises when you average in either time alone or space alone, or both space and time. But now with quadratic operators, we must average in time. And we can see that from the form of the second moment, that because of the dependence of g hat on the wave vectors k1 and k2, if we don't have the f hat factor here, we average only in space, the second moment will diverge. It'll get divergent contributions from the region where vector k1 is equal to minus vector k2, and hence the argument of g hat vanishes. So of course, omega 1 and omega 2 are strictly non-negative. So the argument of f hat will not vanish. Well, that won't happen. So this factor is essential to give a finite fluctuations in a finite second moment. But it does mean that if the temporal scale becomes small in relation to the spatial scale, the fluctuations will become very large. Oops. Just a moment. Did that become, my screen jumped and it became very, very large.
Yes, for everybody, actually.
Okay, just a moment. I have to stop sharing for a moment to fix that. I'm working on a Mac, right? This is a problem that I have, that the touchpad is too sensitive. Now I have to find my presentation.
Let's call it a fluctuation. That's fine.
Yeah, that's right. It's definitely a momentary fluctuation. Now, that I seem to have lost the icon from the top. Seems to have disappeared. Well, okay. The problem is I'm having the problem that once I open my talk, I can't see the button that allows me to share the screen.
Okay. Anybody with technical knowledge can help?
Maybe I can slide it.
What you have to do is to go to the main screen, and then if you move your mouse in the bottom part of the screen, you should see share screen.
I can't do that and have my presentation up at the same time.
No, but then once you do this, your presentation will appear. I think so. Try.
Well, I don't think so, but I'll try sharing the screen and see. Okay, let's try it again and see if that works. No, now it's large again. See, we have the problem.
Okay, now we see it's sort of at a reasonable size.
Now, is it normal size?
Well, it's not presentation style, but
yeah, now it's fine, I think.
Yeah, but okay, you can see it now.
yes.
Okay, well, why don't I just keep it? I'll keep it in this form then.
So it's been 20 minutes, yes, so that I don't interrupt you afterwards.
Okay, so this slide we already. Okay, so as I've already emphasized, these functions should be compactly supported functions, and I'll say a little bit more about these. That compactly supported infinitely differentiable functions have to have Fourier transforms that fall more slowly than exponential, but in general faster than any power. And there's a particular class of such functions we're interested in, where the Fourier transforms fall as a fractional power of an exponential, where that is an exponential of omega to the alpha power, where alpha is a number between 0 and 1. And in fact, if the Fourier transform has this function, this form, then basically the function is something called a Fox H function, or the general function. And typically these have switch-on behavior as t approaches 0 from above as the exponential of a negative power. So a particularly interesting case is alpha equals a half, which switches on as in fact, there's a simple electrical circuit given one of our papers, in which the current switches on with this. So you can actually physically realize this function in the laboratory. So in this case, then this function switches on as an exponential of -1/t near the switch on time. And there are analogous functions in space that can be defined, which also switch on as fractional powers of the k vector. This case is it would be a spherically symmetric function. Okay, so an approximate form for the large moment contributions can be given in terms of this rather messy integral. And I just write this down to point out the only thing that's important here is the large number of factors of the Fourier transforms appear. And because these Fourier transforms fall off at rates that depend upon the parameters alpha and lambda, the size of this integral is going to depend on that. So in particular, the rate of decrease of the probability distribution is going to depend upon the rate of growth of the large moments. And the probability, and hence the probability of a large fluctuation is going to be very sensitive to the switching rate. So 4 dimensions, and we're looking at something with the dimensions of energy density, the appropriate dimensionless variable now is tau to the 4th times the averaged operator. So if we consider the case of time averaging only, then the moments grow as 3n over alpha factorial, which for large n, which would be 6n factorial for alpha equals a half. And the resulting probability distribution will basically fall off as an exponential of a fractional power of the averaged energy density, x to the c, where c is alpha over 3. So that would be 1/6 for alpha equals a half. So you can see then that the form of the switching or sampling functions is very important here. And switching in a finite time interval can produce very large stress tensor fluctuations. So in particular, if alpha equals a half, the probability of just a time averaged energy density fluctuation will fall off like an exponential of the 1/6 power. And to get a feeling for how fast this is falling off, if we let x equals 10 to the 6, this probability is still non-negligible, small but non-negligible. It's about 5 times 10 to the minus 5. So you could certainly imagine experiments could measure events that occur once in a few 100,000 trials. If you compare this with the probability arising from a Gaussian distribution when x is 10 to the 6, that's e to the minus 10 to the 12, which of course is ridiculously small. Okay, if we in addition have spatial averaging, in addition to time averaging, then what we typically find is that the moments first start to grow as they would in the worldline case. With assume the spatial averaging scale is small compared to the temporal scale. So then there's a finite worldline limit, which looks like if you had only time averaging, so the moments grow at this rate. But then after a while, they transition to growing a little more slowly as n over alpha factorial, which is the effect of the space-time averaging rate. So that means that the probability distribution will have a transition from world line behavior to space-time average behavior at some particular point. So in particular, what we expect to find is that initially if x is still large compared to 1, but below this critical transition point, which one can estimate to be about tau over the sampling scale. Unfortunately, I've used different notation here. The sampling scale now is S. What was L a moment ago? But the ratio of the time to the space scale to the third power, if that's large compared to 1, then there's a finite interval in which x is large and the probability distribution is falling off like an exponential of alpha over 3. And then there's a transition to a somewhat more rapid fall off, an exponential of x to the alpha. Of course, this more rapid fall off is just reflecting the physical fact that the spatial averaging will tend to suppress large fluctuations compared to just time averaging alone, but it's still falling more slowly than an exponential. So there's still a possibility of relatively large fluctuations, even in the space-time average limit. And now to go back to the question of when is the probability distribution uniquely defined by the moments, the theorem that's relevant for us is called the stiltshis moment theorem, which says that if you have a probability distribution which is bounded on a half line, and that's the case for probabilities for distributions for classically positive quantities like energy density, because they're strictly 0 below the quantum inequality bound, then there exists a unique probability distribution for a given set of moments, provided the moments grow no faster than 2n factorial for large n. And that will be the case with spatial averaging if alpha is greater than or equal to 1/2. If alpha is less than 1/2, it won't be the case. For alpha greater than or equal to 1/2, it will. However, so even if alpha were less than 1/2, and the moments do not uniquely define the probability distribution, they still, in this case, of course, there can be many different probability distributions that have the same moments. But what happens then is the different distributions typically differ by oscillatory functions. That's the only way that you can have two different probability distributions giving all the same moments. That there are the differences in oscillatory function that cancels out when you integrate it with an integer power of the variable. So the moments still determine the average rate of decrease of the probability distribution, even if they don't uniquely define the probability distribution at individual points. So they still provide important physical information. However, there's an alternative approach to study of the probability distribution, which is numerical diagonalization. Now, this fortunately avoids the uniqueness problems. It is uniquely defined. This was developed in these two papers. And the main idea is to seek a Bogoliubov transformation. So as well known, the Bogoliubov transformation relates two pairs of creation and annihilation operators, the A and A dagger set, which are the physical operators that basically create physical particles and define our vacuum state, to a new set, B and B dagger. And the transformation will be defined in such a way that it diagonalizes the averaged operator, so that the averaged operator T, which is off diagonal in the A basis, becomes diagonal in the B basis, meaning it has only B dagger B terms and possibly a constant in it. So it's very easy to see what the eigenstates of T are. This is this is supposed to be the average operator. I think my bar got lost at some point. So the eigenstates of the average operator are the number eigenstates of the B's here. That is the vacuum state and the various number eigenstates. And we're typically interested in the even number eigenstates because those will be the only ones that will have overlap with the states like the vacuum state that we're interested in. So the probability, once we, so we have now an infinite set of number of eigenstates of T, which are the various possible number eigenstates in the B basis. If we're in the physical vacuum state, in the A basis, the probability of finding a given eigenvalue is just the squared overlap of this eigenstate with the A vacuum. So that allows us to calculate the probability of the different eigenvalues. And then once you have that, you can reconstruct the probability distribution. And this is now unique. There'd be a unique probability distribution associated with each operator in this approach. This approach does not suffer from the ambiguity of the moments approach. However, unfortunately, the actual construction is sufficiently complicated that it has to be numerically. So we actually applied this numerically to the case of normal ordered phi dot squared, using quantization inside of a sphere and a few hundred modes to actually numerically evaluate the eigenvalues. But of course, here we're limited in how far up we can go in the B number basis. We usually go up to we have the vacuum sector, the two particle sector, and a few of the calculations we wound up included 4 and 6 particles in the B basis. And we found that they give very small contributions to the probability. The vacuum and the 2 particle sectors in terms of B give most of the contribution. So this calculation allows us to numerically compute a probability distribution and observe numerically the average, the transition. Slide. This is a sample result that was taken from the 2021 paper that was cited above. So what we're looking at is a log-log plot. So this is the log of minus the log of the probability distribution plotted as a logarithm of x. The bar here just means that we've done some binning of the points. That's you can ignore that. And of course, because we expect p to be the exponential of a fractional power, the log of p will be a straight line. In fact, this gives the red dots are the world line limit. And you can see down here, they lie fairly neatly on a straight line that does in fact have, this is where alpha is 1/2. So it does in fact have the correct slope of about 1/6 predicted. And then there's a transition at some point to the blue region, which then asymptotically approaches another straight line. There's the space-time average limit, which then asymptotically is asymptotic to the exponential of exponential of minus x to the 1/2 here. And there's a finite transition region here. This and you see it occurs somewhere around log x of 8. This vertical dashed line is where our theoretical prediction, if you used tau is set equal to 1 here. So if you use tau over L cubed, that would have risen about here. So what this is saying is that the world line approximation turns out to be better than we expected. we were expecting that the world line approximation would be good at least up to about this point. It's actually a little better than that. It goes out a little further before the spatial averaging starts to become important, but eventually it does. And then we go over into the asymptotically spatially averaged case. And this allows us to estimate the probability of large fluctuations. So in this case, even out in the spatially average case, this is falling off like the exponential of a square root, which can be much, much larger than an exponential. So the probability of very large fluctuations can be non-negligible in physical cases. Okay, so one question here, are these large fluctuations due to states with large occupation numbers or to high frequency modes? Because we're in a bosonic theory, of course, you can get large effects either by having large frequencies or by having very, very large numbers of particles in a given mode. Well, we've made some estimates of the characteristic frequency. This is work that is not yet published, but will be published fairly soon, of the characteristic frequency of the modes that give the dominant contribution. And we've argued that this characteristic frequency grows as the 1/3 power of x in the world line limit. And then it makes a transition to a linear behavior in the space-time average limit. So this and it seems from what we can see is that this is the growth of the frequency is the dominant effect. That is, the large fluctuations are primarily due to high frequency modes, not to large occupation numbers. This will be important in some of the physical applications because this work allows us to estimate. These are by frequency. Now we're interested in the frequency of the A basis, which is the physical basis in which we started. If we're interested in, for example, in forced fluctuations on material objects that are subject to dispersion, then it's important to have an idea of how large how high a frequency of modes contribute, as to see whether this is going to be physically realistic or not. So I'll talk about some of the possible implications of this work. So one is that we already know that in quantum theory, the role of the measurement process is very important. What you see depends a lot on what you're looking for. And this is an especially extreme example of that, where the details of what you find depend very much on the details of how you measure it. And I'll talk about that in an explicit example in a moment. Another feature is the fluctuations are highly non-Gaussian. So that means that the fluctuations of gravity driven by stress tensor fluctuations will also be highly non-Gaussian. This could have implications for cosmology. This could be a source of non-Gaussian density perturbations in cosmological models coming from the tail of the probability distribution. It also means possibly large radiation pressure fluctuations on material objects such as charged particles or atoms. That is another place where one might try to look for these fluctuation effects in the laboratory. There are possible experiments that might be done to look at these. And then an especially interesting case I'll spend a few minutes talking about are light scattering by density fluctuations in a fluid, which is a very useful model. So if we consider
let me remind you that it's been already 40 minutes. You can go on for a few more minutes if you have to.
I'll finish fairly quickly then.
Okay, no problem.
Okay.
Thank you.
So the density perturbations, in fact, can be shown to be proportional. This is previous work done by many other people. In fact, you even find this in one of the Landau-Lifshitz books, that the density perturbation fluctuations due to phonon effects in a fluid are proportional to the time derivative of a massless scalar field, but which looks just like the relativistic field, but with the speed of light replaced by the speed of sound. And if we want to consider light fluctuations by a density of perturbation, the scattering is going to be proportional to the square of the density. That's simply because, say, if you scatter light off of a classical density variation, this is a coherent process. The scattered electric field will be linear in the density variation, but the scattered power will be quadratic. So that means that the mean number of scattered photons will be proportional to the fluctuation, or the fluctuations in the number of photons will be proportional to fluctuations in phi dot squared. And of course, if you send a pulse of light through the fluid, it travels many orders of magnitude faster than the speed of sound. So in terms of a sound cone diagram, this is traveling at space-like intervals relative to the sound cone, which is this field is like a relativistic field, but in this modified space-time. Send a finite light pulse, which soon will be described by a compactly supported function, which was the experimenter control the form, the shape of the pulse and its duration. And then you have a detector with an aperture. The scattered photons that will be seen by the detector as the pulse goes by will be emitted from this red region, which is the overlap between the aperture of the detector and the wave packet as it goes through. Will be some finite region. So the experiment will be to count photons as a sequence of pulses go by. And you should see fluctuations of these number of photons. And the fluctuations will reflect the fluctuations of normal ordered phi dot squared in the relativistic theory. So in fact, if you plot the expected number of photons, the number of photons you get in a sequence of experiments, that histogram should in fact recreate the probability distribution for phi dot squared. So this is a potential way in the laboratory to actually go and measure the effect that we're talking about. So since we're running out of time, I'll just quickly summarize here. So the probability distribution for stress tensor fluctuations requires averaging at least in time. They fall more slowly than exponentially, leading to possible dominance of vacuum fluctuations. And we need measurements in a finite interval, which lead to especially slow fall off due to the slow fall off of the Fourier transforms. And we'll also need some spatial averaging. And all of this means that there are possible observable effects in various contexts of these large vacuum fluctuations, maybe in cosmology, radiation pressure fluctuations, or as I've just described, light scattering in matter. So with that note, I'll stop.
Okay, thank you very much for your talk. And if there is any question, okay. Morgan Lynch was first, so please.
Okay. Well, thank you very much for a very interesting talk. I was a little intrigued with this, that you showed that you have the large scale fluctuations are dominated by high frequency modes, not by large populations of low frequency modes, and then you have these not so much an exponential suppression of these large fluctuations, but I guess e to the minus x to alpha, or so it's like a
right. It changes the exponent, the exponent inside the exponent.
Yeah. And so I just have to ask if I mean, is this something that can like temper this cosmological constant problem? like, this with the 120 orders of magnitude that you get from, summing over all of these quantum fluctuations? Is this something that can, I guess, regularize this?
I'm not so sure. Of course, here we're talking about energy density fluctuations in a small region. I mean,
Yeah.
of course, the connection between the cosmological constant and vacuum energy is already a little bit controversial to begin with. But it would also have to be a mean vacuum energy, some kind of expectation, because we're dealing with an average energy over a large region of space. So I don't think what I'm talking about is particularly relevant for that.
Okay. Okay.
I'm talking about energy density average in a small finite region.
I see. Okay. Thank you.
Okay. Any more questions?
Professor Ford, thank you so much for your talk. I'm interested in the whether your recent insights could maybe be extended to shed light on negative energy flux.
Well, yeah, actually, they do, because in fact, as I talked about earlier in my talk, the lower end of the probability distribution is telling you about the probability of getting negative fluctuations. So in fact, if you look at the left end, the small x end of the probability distribution is exactly talking about near the quantum inequality bound and the probability of getting various amounts of negative energy in a fluctuation in the vacuum state. It is relevant to that.
And actually radiated rather than just the density.
Well, it could be any quadratic operator. So something like of course, flux doesn't have a quantum inequality bound, because it can go in either direction, even classically. So there's no lower bound on it. But you can still get fluctuations. So for example, you compare a state where all the particles are moving to the right. But if you measure the instantaneous flux, you could find the flux the energy flux to be moving to the left instantaneously. And that's essentially the flux equivalent of a negative energy fluctuation. And the probability of that would also be described by this type of distribution.
Thank you.
So as far as I've seen, what you're doing is an average in time and space, but that doesn't seem to be Lorentz invariant. So in which frame are you doing those averages?
Okay, so that's a good question. You need to pick a particular frame, and the viewpoint that we're taking is that this should be all of these averaging are basically done by the experimenter. The experimenter is basically setting up a situation to try to measure, for example, energy density or some other quantity. So essentially, it's the rest frame of the laboratory.
Okay. So it's at the proper time of the detector that you're using.
That's right. It's whatever the detector that you're using, that Lorentz frame.